In these figures, we'll examine the factors that affect systemic arterial blood pressure. And systemic arterial blood pressure varies over time due to intermittent cardiac output. So we'll see a trace of blood pressure looking a bit like this, where pressure falls, and then it spikes quickly, and then it'll fall slowly, and then it spikes quickly, over and over again. And so what we're going to do is we're going to take one of these traces and we're going to blow it up down here, basically going from here to about here, and examine that more thoroughly down below. Now, before we do that, let's look in the upper right here and get more of a general idea of how blood pressure varies over time and why. And so we have a schematic heart with a single artery coming out of it, sort of arbitrary artery coming out of it. We would measure our blood pressure in this artery, and what we'd find is that the blood pressure is proportional to the volume of blood in that arterial circuit at any given moment. Now, that volume does not stay constant. It's constantly changing. And it's changing because our cardiac output, our inflow, is intermittent. We eject blood intermittently, and then our heart has to relax and fill again before it ejects blood again. However, on the other end of the circuit here, our arterial runoff into our capillary beds is continuous. And therefore, our volume will rise and fall, and therefore our blood pressure will rise and fall due to this continuous runoff as well as the intermittent input. And so during ejection, the input rate will exceed the output rate and pressure will rise. And then during diastole, the relaxation phase of the heart, the runoff continues and there is no input, and so volume will fall and pressure will fall. Well, why do we care? Why are we worried about this? Well, we're worried because pressure drives flow. As you can see here in Poiseuille's law, flow, Q, through any given vessel is equal to the pressure gradient along that vessel divided by the resistance of that vessel. And what we see is that the pressure gradient in that vessel is proportional to the flow. And so we have to maintain a certain amount of pressure to drive flow across the resistance of that vessel. So pressure is very important to maintaining aerobic respiration and avoiding very deleterious effects of low blood flow. Now, we'll see here above, if we solve Poiseuille's law for pressure and put the terms in for the entire systemic circuit, blood pressure for delta P, cardiac output for flow, and total peripheral resistance for resistance, just solving for this delta P, blood pressure here, we find that blood pressure equals cardiac output times that total peripheral resistance. Well, remember, our inflow is our cardiac output, and our outflow is determined by that total peripheral resistance. The higher the resistance, the slower the outflow, the slower the runoff, and the more blood we would trap inside here, increasing our pressure, right? If this goes up, the blood pressure would go up. If inflow goes up, our blood pressure would go up. Okay, great. Now let's come over here to this individual trace and examine what's going on. And so during diastole, what we see is that the pressure is falling, once again, because our runoff continues and there is no input. Cardiac output is not occurring. Then we enter the systolic phase, where our stroke volume is being ejected. Well, immediately we're going to start to have an increase in pressure as the inflow now exceeds the outflow. Pressure is going to rise to a peak here. That's called the systolic pressure. Then we'll start to lose pressure as our ventricle starts to relax. We'll continue to eject for just a moment due to the inertia of the blood moving. We're going to get a dicrotic notch, this little blip in the pressure here. That occurs because the aortic valve closes when the ventricular pressure falls below the pressure in that aorta. Blood actually flows backwards for just a second. We get a little blip in the pressure, and then we're in our diastolic phase, and our pressure continues to fall for a much more prolonged period than during systole, right? The diastole phase is longer. And we fall all the way down to our diastolic pressure, the lowest pressure in that arterial circuit. Again, just before we start to eject blood again with our cardiac output, enhancing our arterial volume and therefore pressure. Now, a couple other things to note. The pulse pressure is simply the difference between the systolic and the diastolic pressure. And the mean arterial pressure is the diastolic pressure plus 1/3 of the pulse pressure. Now, that might seem odd. You would think that it would be halfway in between. In other words, plus half of the pulse pressure would put it halfway between systolic and diastolic. But that's not the case over time, because as you can see, we spend more time in diastole than we do at these peak pressures during systole. And so over time, we're a little closer to the diastolic pressure with our mean than we are to the systolic pressure.